Hey y'all, this is Professor Wyman with a quick video on one versus two-tailed hypothesis testing. And I am really going to focus on a very simple explanation, but this applies to what I hope is a simple explanation. What applies to a t-test, z-test, Pearson's R, the test that we're doing in class right now. So first of all, we start with an alternative hypothesis or a research hypothesis. So in this example, what you're looking for to decide if you need to conduct a one or a two-tailed test is what the direction of the signs tell you about your hypotheses. So this is our alternative hypothesis, and this can also be denoted as an H sub A. But this alternative hypothesis is that mean one does not equal mean two. So it could be that mean one is greater than mean two, or it could be that mean two is greater than mean one. So the idea here is that you're looking for any direction that's so extreme for your observed value that we can say that this null hypothesis, that nothing is happening, that there's no difference between those means, that's statistically significant, that it's a large enough difference to suggest there's a real relationship in the population. So when we go into this process, once you've determined that you have a two-tailed test, what this means when we say two-tailed test, it's that we're looking at both directions of these of this relationship. Now, when we break up our distribution into having rejection regions and then this fail to reject region, what we need to determine what those probabilities are in those regions is actually our alpha, which is our significance level. So alpha is typically 0.05. We determine this, first of all, 0.05 is just the standard most commonly, but we determine this by deciding how much error, probability of error we're willing to expect or accept, I guess would be a better term for it. So basically, if you want to be more confident that you are correct when you reject the null hypothesis, then you want your alpha to be smaller. So this 0.05 represents a 5% probability that if we reject the null hypothesis, we've made a type 1 error. We've rejected it when we shouldn't have. So this significance level is what determines how large your rejection region is. So if our alpha is 0.05, in a two-tailed test, you're going to split it between the two tails. So these are our tails. So here we would say that this rejection region is the most extreme 0.025 of the distribution, or 2.5% is the way that you would interpret that if you wanted to think about it in percentages. And then over on this side would be the most extreme 0.025 in the other direction. So this is where mean one is greater than mean two. And this is where mean two is greater than mean one. So when we're doing a two-tailed test, we're looking for our observed value to fall in the most extreme 0.025 or 2.5% on either side of the distribution. And then this fail to reject region is just 1 minus alpha, which is 0.95 or 95%. So if your critical value is what you're using to determine your cutoff point here, then you would need your value to be higher. You would need it to be more extreme than the critical value here. If you are using a statistical program like SPSS or Jamovi or whatever it might be, then you would calculate your p-value, and the p-value tells you if if the likelihood of your observed value is so low that we would consider it to be more extreme than our alpha, where we say our p-value is less than alpha or alpha of 0.05, then we would reject the null hypothesis. So this is our two-tailed test. Now let's go ahead and talk about one-tailed. And so again, it's going to be based on your hypothesis. So in this example, you can see that there's a directionality to the hypothesis. And that's how you determine, again, what test you're going to run. So in this example, I've made a specific statement that mean 1 is going to be greater than mean 2. So I'm only looking in one direction. And then my null hypothesis is going to be the opposite, which is that mean 1 is less than or equal to. So I don't have the option of saying that if I find that mean 1 is less than mean 2 and it's statistically significant, I don't get to say that. I, as the researcher, have chosen that I'm looking for a specific direction to my relationship. And so what that means is that I'm looking for one side of this distribution, and that's my rejection region. So it doesn't matter if I get an extreme low score indicating that mean 2 is actually larger than mean 1. I'm looking for a specific direction. So I'm only looking for that specific relationship here. Now, this gives us more statistical power. And what I mean by that is that our alpha is 0.05. We're going to continue with alpha equals 0.05. And so when that's the case, we're looking for 0.05 all in one side of this distribution. So our critical value here is actually smaller. And so it needs to be a smaller observed value to be statistically significant, because we're looking for all of our possible rejection region on one side. So it's actually easier to reject the null hypothesis if you're doing a one-tailed test. And you'll find that when you are making hypotheses, it's more likely that you're going to have a one-tailed test, that you think something specific is going to happen. It's less likely that you're going to say, oh, I think there's some difference, I just don't know what it is. Typically, you go into a study anticipating that there's a specific difference. So that is what the difference is between the one and two-tailed tests. If you want more information on p-values, I do have a different p-value video that you can view that talks about p-values and critical values.